I'm going to run through a quick example problem here. This is R2 from the review section of Chapter 7. So I encourage you to try it on your own, but I will be doing it here. I've written out some of the problem to keep this video short, and I'll run through it. The first two I'm going to actually do by hand though. So we have this. It says a type of jet engine where air goes in, and the more air that's rammed in, the more power the engine generates. So part A here tells us that we are going to assume that the rate at which the plane's speed changes is directly proportional to its speed, and then we want to write out a differential equation. So the rate at which the plane's speed changes is ds dt. Okay, and then it says that it's directly proportional to the speed. Write some constant k. This will be our speed. So the rate of change of the speed is directly proportional to speed. So that's our differential equation. Right there. Part B asks us to solve that differential equation. So we're going to do that here. ds dt equals ks. So our trick is we're always going to separate variables. So I'm going to divide the s over. We'll have 1 over s ds is equal to, and I'm multiplying the dt over. So we'll have k dt. Now I'm going to integrate each side. Integral of this 1 over s, we're going to get natural log of the absolute value of s. We'll do a plus c, but I'm going to put that on this other side here. Constant minus a constant is another constant. Integral of k is going to be plus c, or combined constant of the two. Now to get rid of the natural log, I'm going to raise each side to the power of e. E to the ln of absolute value of s is just going to be s. Describe what happens to the absolute value sign. E is always going to be a positive function, e to anything. Any positive value, we know s is going to be positive because we don't have a negative speed. So that's where that goes away. Then we'll have e to the k t plus c. In rules of exponents, I can rewrite this as e to the kt, e to the c times e to the c. And I will call this here, which is another constant, c1. In the end, we've got s equals c1 e to the kt. Solution. General solution. Okay, this is where I've started writing stuff out before to keep the video short. Part C asks us to evaluate the constants in the equation by putting in this boundary value information. So we know that the speed is 400 when our time is at 0 seconds. So this is piece 1 of information. Piece 2 of information we know is that at 40 seconds our speed is 500. So using piece of information 1, I'm going to plug in 400 for s and 0 for t. So we get c1 then equals 400. So our new equation is going to be s equals 400 e to the kt. Right, now using our second piece of information, we can plug in 500 for s into this new equation, and 400 was our c1. So, and 500 for s, and t is going to be 40. So we'll have 500 equals 400 e to the 40k. Dividing both sides by 400, I'm going to get 5/4 equals e to the 40k. Taking the natural log of each side to get rid of that e, I get natural log of 5/4 equals 40k. And then finally divide by 40 to get k. So we get k equals about 0.006. So our final equation is right down here. S of t equals 400 e to the 0.006 t. That's our particular solution. Finally, part D here asks us when the plane will reach the speed of sound, which is 750 miles per hour. So we're given that s equals 750 and we want to find what t is. Well, we just plug in 750 for s, t we just leave as t, dividing both sides by 400 to isolate the e, taking the natural log, and then finally dividing by 0.006 to get t, and it's going to be at 104.768 about seconds.